magnetic field at an equatorial line of a bar magnet. So we know a bar magnet is like it is a magnetic dipole which consists of two equal and opposite poles. Okay, so let us say that this is a bar magnet which constitutes of south pole and north pole, and these two poles they are at a distance 2l. Okay, now I want to determine the magnetic field, say at this point P, okay, which is a point on the equatorial line. So you know equatorial line, it is a line which is passing perpendicular to the center of the dipole. Alright, so like before, right, we will consider a unit north pole placed at this point P. So this unit north pole, it will experience two magnetic forces. One is from the south pole and the other is from the north pole. Suppose Fs is the magnetic force which is experienced by a unit north pole at P due to the south pole. So because this is north, this is south, so the force will be attractive. So your Fs will be acting along Ps. Okay, alright. Now, let us say that this distance PO here, it is equals to R. Then I will write the magnitude of this force as mu naught upon 4 pi Qm upon what is the square of the distance between this point and this point? It is Ps square. I hope you still remember this Qm, it is actually the strength of the poles. Okay, so at this point the magnitude, the magnitude of the south pole, it is Qm, right? Actually this might, when you take about the direction, it means minus Qm, but only magnitude is just Qm. And the directions of this, it is acting along which direction? Along Ps. Or I can say this Fs is equals to mu naught upon 4 pi Qm upon, instead of Ps, I will write how much? Now this Ps, because this is a right angle triangle, so Ps square mean SO square plus OP square. But SO is equals to L, so I will write here as like this, R square plus L square. So this is my equation 1. Similarly, when you look at this point P, right, now the force at this point P due to the north pole. So at point P again we have a north pole. So this north pole will experience, a repulsive force in this way. And let's say this force is Fn. Okay. So therefore Fn, it should be equals to mu naught upon 4 pi magnitude of the pole upon square of the distance. Again, right, square of the distance, it is Pn square. But Pn square, when you find out using Pythagoras theorem, you will get R square plus L square. Okay, this is my equation number 2. And this force is acting along which direction? It is acting along NP. So along NP. Okay. Now look at this figure. The two forces Fs and Fn, they are acting, in different direction. So therefore, we need to resolve them into two rectangular components. When you look at Fs, then if you resolve this Fs into two rectangular components, then, okay, for that, let me just name first this angle as theta, this angle as theta. So if this is my horizontal, so this angle also will be theta, okay? Because this angle with this angle, they are alternate interior angle, so, they are equals to each other. Similarly, if this angle is theta, then this one also will be theta. Okay. Now, if you resolve this Fs into two rectangular component, then along this line, you will get Fs cos theta. And the component of Fs, right, along y-axis, it is Fs sine theta. Okay. So similarly, when you resolve this Fn into two rectangular component, you will get Fn cos theta along this direction, and above, right, I mean in the vertical direction, you will get Fn sine theta. Okay. Now, because the magnitude of the two forces, sorry, I made a mistake. This is not Fs, but this is Fn. Because the magnitude of the two forces are equal in this case, so hence, right, these two components, Fn sine theta and Fs sine theta, they are acting, in opposite direction. So therefore, they will cancel out each other effect. But the two components, right, like Fs sine theta and Fn cos theta, they are acting along the same line. So therefore, these components now, they will give you the total magnetic field at a point P. So what is the total magnetic field? The total magnetic field, let me write as B equatorial or BEQ. This will be equals to Fn cos theta plus Fs sine theta, sorry, Fs cos theta, and this net magnetic field, it should be acting along which direction? It should be acting along this direction. Let me name this as okay, let me name as Q. So this will be acting along PQ. Alright. Or I can say my B equatorial here is equals to, because Fn and Fs, right, the magnitude of these two are same. So in place of Fs, I will write Fn. So if you write Fn, then this become Fn cos theta. So when you add with Fn cos theta, you'll get 2 Fn cos theta. Okay. Or B equatorial is equals to 2. How much is my Fn? It is mu naught upon 4 pi Qm upon r square plus L square. That is the value of Fn. But when you take this cos theta, right? Let's say consider this triangle. Cos means base upon hypo, which means L upon this PS. Okay, right? Or I can say first, like in this right angle triangle, when you take cos theta, you'll get SO upon PS. Okay. B equatorial now, it is equals to 2 mu naught upon 4 pi Qm upon r square plus L square times, how much is SO? Your SO is small m. And how much is PS? Okay, because we know PS square is equals to L square plus R square. So when you say just PS, it means L square plus R square to the power half. So instead of PF, I'll write R square plus L square to the power half. Okay. Now, this denominator, okay, this is factor 2, I'll write here. Okay. Now this 2 I have shifted, I multiply with L, it's the same thing only. Now look at the denominator, we have R square plus L square, the power is 1. This is R square plus L square, the power is half. So when you multiply the two, the power should be added. So when you add the powers, then you'll get R square plus L square to the power 3 by 2. Okay. Or I can say that this net field at a point P on the equatorial line, it is equals to mu naught upon 4 pi Qm times 2L. A pole times the distance, that is magnetic dipole moment, which is denoted by small m, upon r square plus L square to the power 3 upon 2. Okay. Do I miss out anything here? Okay, let me check. Okay, this is fine. I didn't miss anything. So now, let us come to a special case, that is for a short bar magnet. So like before, for a short bar magnet, or we can say for a short magnetic dipole. Okay, right? This r square can be neglected. Okay, can be neglected compared to, sorry, L square can be neglected compared to R square. So if we neglect this L square, then you will have B equatorial is equals to just mu naught upon 4 pi m upon, now if you neglect L square, then you'll have just R square to the power 3 by 2. Now this 2 with this 2 cancel, so your B equatorial is equals to mu naught upon 4 pi m upon R to the power 3. So this is the magnetic field at the equatorial point of a bar magnet. Alright, now where is the directions of this magnetic field? The directions of this magnetic field is clearly seen here, right? It is acting along PQ. So along PQ, that means it is directed right from North Pole to South Pole. From North Pole to South Pole. This is the net magnetic field. So from North Pole to South Pole, it means it is opposite to the magnetic dipole moment, because magnetic dipole moment is directed from south to north. Okay, so therefore please note down here that the directions of the net magnetic field at the point P, it is opposite to the magnetic dipole moment. Okay, now if you remember in the previous lecture video, we have seen that the magnetic field, right, on the action line is equals to how much? Mu naught upon 4 pi twice m upon r cube. And my B equatorial here, or I can say this B axial, it is equals to, if you take this factor 2 in front like this, then you'll have mu naught upon 4 pi m upon r cube. Or this B axial, it is equals to how much? It is equals to 2, and this value mu naught upon 4 pi m upon r cube, it is equals to B equatorial. So please note down this equation. Okay, that means the magnetic field at the axial point of a bar magnet is equals to twice the magnetic field at the equatorial points of a